Okay, so there is the main thing that we need to do is what is the gamma of 1/2. It means we can also define the gamma function of some sort of fractions. So how to evaluate this thing is another idea, but the value of this particular thing is square root of pi. This is the good thing. We can evaluate this. We have solved one Gaussian integral when we are doing the course on multivariate. We have evaluated that integral. With the help of that integral, you can say that the value of gamma of 1/2 is going to be square root of pi. Okay, you can simply put in this formula, you can put gamma of 1/2. Okay, let us apply this formula, then let's see what happens. I am applying this formula and not the previous one. Gamma of 1/2 is going to be 0 to infinity. I put here 1/2. 1/2 times 2, 1, 1 minus 1, 0. So this is cancelled. So I am left with. So gamma of 1/2 is square root of pi. So you can say that this integral also equals the square root of pi. And sometimes in exams you are asked about this integral e power minus y square dy. Its value is going to be square root of pi by 2. 0 to infinity e power minus y square dy is square root of pi by 2. So there is one thing else. Sometimes the limit is 0 to infinity, but the problematic situation is sometimes you are given limit from minus infinity to infinity. So its answer is going to be the double of this, that is square root of pi. Because why? Because this function is, I think, an even function. From left and right its behavior is same. That's why this is like that. So these are some things that we should keep in our mind when we are going to evaluate the value of gamma function for different numbers. We know very well it is good for natural numbers, but it is valid for fractions as well. Okay, how about evaluating this thing? Gamma of 3/2. How to evaluate this thing? Gamma of 3/2. You can apply what we call recurrence relation, and you just remove 1 from this. It means subtract 1. 3 by 2 minus 1 becomes 1 by 2. It means just subtract 1. So this is equal to 1/2 times gamma of 1/2. And we know very well gamma of 1/2 is the square root of pi. So the value of this is going to be square root of pi by 2. Value of gamma of 3/2 is going to be this. Similarly, we can evaluate gamma of 5/2, and just you have to reduce 1, that becomes 3/2 gamma of 3/2. And this 3/2 remains same. Gamma of 3/2 is going to be square root of pi by 2. So this becomes 3 square root of pi divided by 4. So you can evaluate these all the things. So you can evaluate gamma of n plus 1/2 in general, where n is any natural number, and the formula for this is 1, 3, 5 up to 2n minus 1. It means the product of all the odd numbers divided by 2 power n times square root of pi. So we can evaluate with the help of this formula as well. But it is very difficult to memorize this formula, so we can just keep this recurrence relation in mind, and we can evaluate the things easily.
So what happens if minus 1 come out?
Yes, we can do the same thing, like gamma of minus 1/2. So let us do this. Let's do it. Gamma of minus 1/2. But it is not going to be okay. Can I apply recurrence relation on this? I have to subtract 1. What it becomes?
Minus 1/2.
Minus 1/2. So you know very well gamma of z plus 1 is z times gamma of z. So you subtract 1, this becomes minus 1 half gamma of minus 1 half. So you can do like this, minus 1 half gamma of minus 1 half. Now gamma of 1 half is the square root of pi. You take minus here and you multiply 2. This is the value of gamma of minus 1. So we can evaluate these, but the problem would be, what is gamma of 1 by 3? We don't have exact formula for this, but it has a value which is going to be some sort of value in decimals. It has value, but we don't know what is going to be that value because we don't have exact formula for this 1 over 3. If this denominator is going to be 2, then we are okay with this. If the denominator is 3, 4, 5, then we are not okay with this. But you know very well, this is not defined, because I told you already this is not defined for negative integers as well as 0. This is not defined. But rest of the things we can evaluate with the help of different formulas. Okay, any question up to here? This one. We need to evaluate gamma of minus 1 half. So we can take help of gamma of 1 half. So we can apply this formula. This formula tells that just reduce 1. Z plus 1, you reduce 1, it becomes Z. 1 half, you reduce 1, it becomes minus 1 half. So this is minus 1 half, gamma of minus 1 half. So you just put this value and you are done. Okay, so only one or two other things related to this function, then we are going to move towards beta function. There are lots of things, but these are advanced which are never asked in our examination, so we are not supposed to discuss these things. There is a formula, what we call the duplication formula. Duplication formula, that is, how do we define gamma of 2z? Because we know very well gamma of z is something, we know that thing, but what is gamma of 2z? So that is simply defined in this way: 2 power 2z minus 1 divided by square root of pi gamma of z times gamma of z plus 1, z plus 1 half. This is what we call the duplication formula. We can apply this when we are going to find out the gamma of twice of something. We can apply this one, but it is mostly never asked. It is mostly never asked in different exams. You know what is Euler's constant? What is Euler's constant? Euler's constant is E. Everyone knows the value is like this, 2.718 and so on. But basically its name is not Euler's constant. Euler's constant is something else. It is mistakenly used. It's a number, gamma. So to remove the confusion, it was named something else, because people were mainly use E to be Euler's constant. So if we call this gamma to be Euler's constant, this is a problem. So it is called Euler and Mascheroni constant. Let me see there. Yes, Mascheroni constant. It is somehow related to this context, that's why I am going to tell you. Its value is 0.577 and so on. But how it is defined? Do you know what is the definition of log x?
It is simply exponential, inverse of exponential.
Definition. If someone asks what is the definition of log x, that's actually you take function 1 over x, you take 1 over t, and you integrate with respect to dt, and you evaluate it from, I think, 1 to x. And this is the definition of logarithmic function. This is the definition. We can say it's inverse of exponential and so on, but this is basically the definition of logarithmic function. What does it tell? You have a function 1 over t. You know very well 1 over t somehow looks like this. It goes near and near to 0, and exactly at 0 it explodes towards infinity, and you are calculating its area from 1 to, let's say this is 1, so you are calculating this area towards a fixed x, and then this area is called log x. Okay, then what is this? Let's say k 1 over t. What is this? This is a sum. First of all, you put here 1. It means 1 over 1. Then 1 over 2. Then 1 over 3 and so on. So this is going to be a sum. Can I denote this sum in this way? This is my 1 over 1. And let's say this area is 1 over 2, and this area is 1 over 3, and this area is 1 over 4 and so on. Can you compare which area is bigger and which area is smaller out of these two? Which area is bigger and which area is smaller? I gave you two areas, 1 to t from 1 to x and k equals 1 to n. You can see these areas. Which one is smaller and which one is bigger? This log x area, this portion is not included. This starts from 1 and this is the area. So it starts from 1 and this is the area. And this area is only these parts are removed and these parts are becoming smaller and smaller and smaller. But this whole chunk is involved in this one. So this looks like a bigger area as compared to this. The problem is this area starts from 1 and this portion is not included in this area. But in this particular area, this whole portion is included at first. Then seemingly this area is bigger than this area. So what we do basically, we take this sum of 1 over k when k runs from 1 to n and we subtract log n out of it. We take this area, we subtract, let's say this is log n, and what we do, we apply limit n goes to infinity, and then we get what we call the Euler-Masoni constant. We subtract and we take as n goes to infinity, then we get this constant and its value is 0.577 and so on. And this is an irrational number. Being irrational of this number is a conjecture, and you know very well what do we mean by conjecture. Conjecture means it is no proof for now that whether it is a rational number or irrational number. But once we prove it, we get some good results. Okay, one last thing about gamma function, then we are going towards the beta function. And the last thing is what we call the Stirling's formula. Stirling's formula, and it is the formula which is used to find out the factorial for very large values. For example, when you find 100 factorial, it's going to be very difficult task to calculate. Even in computers, 100 factorial, 200 factorial is going to be a very difficult job. But we can find out that z factorial, and you know very well z factorial is equal to gamma of z plus 1 is equal to square root of 2 pi and z power z plus 1 half e raised to minus t. This is what we call the Stirling's formula, which is very helpful to evaluate the factorial for very large values. When you are given a very large number, you can evaluate with the help of this particular formula. Shall I remove this one? We have this constant, it's very useful, but we are not going in depth. That's why I told you what do we mean by this thing. Sometimes we are interested in, I think, what is the derivative of gamma function. And when you differentiate a gamma function with respect to z, then we involve these particular things. And this thing is used when you are finding what's, let's say, the Laplace transform of gamma function. And what is going to be the Laplace transform, not specifically this one because this is very difficult, but what is the Laplace transform of log z or log t, because we have never seen what is the Laplace transform of log t, but we can find out the Laplace transform of logarithmic function. We know very well we can find out Laplace transform of polynomials, sinusoidal functions, we can find out Laplace transform of exponential functions and so on, but you can do this thing as well. So this number is used over there. When you see just the book of S.M. Yusuf, it's very last chapter in the new edition. Last chapter is, I think, Laplace transforms. You will see what is the Laplace transform of log z, and when you evaluate this one, you will find there's a constant this thing over there. You can see this thing. But when we are going in depth, we will be simply wasting our time on these things. We are only concerned towards the things which are required for our exams. So the second thing is what we call beta function. And beta function, what's the name? Other name? Euler's integral of first kind. You can verify these things, that which one is first and which one is second, but these are named like this. Euler's integral of first kind and Euler's integral of second kind. This is Euler's integral of first kind. So how it is defined? So for beta function we need two parameters. In some books you will see m and in some books you will see p and q. In some books you will see a and b, depends upon the context of the book. And the limit of integration is going to be 0 to 1 and t power a minus 1 and 1 minus t power b minus 1 dt. And when it is valid, when a is greater than 0 and b is greater than 0. These should be greater than 0. Okay, so the other form of this beta function, when you substitute t equals u over 1 plus u, it means this is a substitution, then you get another form of beta function, that is beta of a comma b is equal to integral from 0 to infinity. Now it's going to be infinity. And u power a minus 1 plus u power a plus b and du, again a is greater than 0 and b is greater than 0. This is just the equivalent form of beta function, it's nothing else. So only we are concerned about this particular form of beta function. Okay, you can evaluate beta evaluated at different values, like what is going to be beta of 1 comma 1. Since it is valid for all the values greater than 0, so I can evaluate beta of 1 comma 1 easily. Just you put here a is equal to 1 and b is equal to 1, this power becomes 0, so these are reduced. Now we are left with 0 to 1 dt. So this becomes t from 0 to 1, so our answer is 1. Similarly, you can evaluate what is beta of 2 comma 2 and what is beta of 2 comma 1, and what is beta of 1 comma 2, and so on. These things are easily evaluated with the help of this integral. Only you should know how to evaluate integrals. Then this thing is not a big deal. But the good thing about this is the relationship between gamma function and beta function. That's very good thing that we can see. But we are going to that before that we are going to write another relationship between gamma and beta function. That's something that is very good. And there is another form of beta function, and that can easily be achieved from this one when you substitute t is equal to sine square theta. You just put here t is equal to sine square theta and you will get something different form of beta function, what we call the trigonometric form of beta function. You just put t and you evaluate dt, you put in that one, then you will get something that is totally new. Beta of a comma b is, now it becomes 2 times integral from 0 to pi by 2. The limit of integration is 0 to 1. Now it becomes 0 to pi by 2. This is something very good. And sine 2a minus 1 theta and cos 2b minus 1 theta and d theta. So now you can see that we can evaluate lots of things with the help of this particular trigonometric form of beta function. And if it is okay, then we can do lots of things. The question is how to evaluate this thing, beta of 1/2 and 1/2. Beta of 1/2, 1/2. You have standard definition. In that one, we are putting a is equal to 1/2. And what is the standard definition? Integral 0 to 1 t a minus 1 and 1 minus t b minus 1 dt. Are you okay up to here? Because we know very well this is the definition. What am I doing? I am just removing this and just substituting 1/2. So this will be 0 to 1, 1/2 minus 1 minus 1/2, and I can take it down, it becomes plus 1/2, and this is going to be plus 1/2 as well. And you know very well we can write this thing as 1 over the square root of t times t plus 1 dt. The question is how to evaluate this thing. It's very difficult. If you know the integration, we cannot evaluate this simply. So I am evaluating beta of 1/2, 1/2. This is something that is going to be very difficult. So I am not using that particular form. Now I am using this form, and let's see what happens. I will be having the same value, just the integral representation would be different. So 1/2, 1/2. Now do something else. That is this. Put 1/2 in this one. 2 times 0 to pi by 2. Okay? Put 1/2 here. 2 times 1/2 is 1. 1 minus 1, 0. 2 times 1/2, 1. 1 minus 1, 0. Sine power 0 is 1. So this becomes 1, this becomes 1. You are left with only d theta. Sorry. Yes, d theta. So you are left with only this one. And now you can see it's very easy to value. Now using this thing, beta function of 1/2, 1/2 is something very difficult, but using this thing you know very well. The integration is going to be theta and the limits are 0 to pi by 2. You just put the limit and your answer is going to be pi. Using this, very difficult, using this is going to be pi. Now we will be using this thing, beta of 1/2, 1/2. Just keep in your mind that's going to be equal to pi. We will be using this thing very soon.
यहाँ पे माइनस आएगा ना?
Where?
जब आप 1/t पावर 1 over 2 को मल्टीप्लाई करें 1 माइनस तो a b यहाँ पे सब माइनस आना।
Where?
नहीं इधर। तो जब आप मल्टीप्लाई करेंगे नहीं सर इसी को 1/t पावर 1 over 2 को जब हम मल्टीप्लाई करेंगे 1 minus t पावर 1 over 2 a पावर n और b पावर n वाला फार्मूला लगा रहे हैं यहाँ पे। तो यहाँ पे t टाइम t माइनस वाला आना चाहिए।
हाँ between gamma and beta function. So I am simply writing the formula beta of a comma b is gamma of a plus b. So now you can see we can define a relationship between beta and gamma function, and we can do its proof as well, but it's not something that's necessary here because it will take a lot of time. Now what am I doing? I am applying this thing to get some good results. What am I doing? I'm just substituting a equals 1/2 and b equals 1/2. Can I do this? I can do this easily. Gamma of 1/2 plus 1/2. What is the value of this thing? We know very well the value is pi. And this thing becomes denominator is gamma of 1. And this thing becomes gamma of 1/2 whole square. What is gamma of 1? It's 1. Just remove this. So gamma of 1/2 whole square equals pi. So what do? You just take square root, gets cancelled. So it's gamma of 1/2 is going to be square root of pi. So we know that gamma of 1/2 is this, but we can evaluate this value from beta function as well. So this is going to be something very easy. Only what we should do, we should know the trigonometric form of beta function. We know very well. Evaluate this thing, and second thing is only we should know this formula. Then we are done with this thing. Okay, any question from here up to now?
Do we have some special properties for beta function? This is the relation between beta and
one thing is that when you define beta function in the sense of gamma function, then all the properties of gamma can be transferred in this one as well. You know very well this is like gamma times gamma, then you can apply these properties. Once you can convert beta function into gamma function, then you can do all the things. So it's something very good. Like if you want to evaluate, let's say beta of 3/2 and 1/2, for example, can we do this? The thing is that if you can do this, then you can do that one as well. So let us do this if we want to. Gamma of, because I can convert this using this formula, and gamma of 1/2, gamma of 3/2 plus 1/2. You know very well gamma of 3/2 is going to be 1/2 times gamma of 1/2 using what we call the recurrence relation. And this is gamma of 1/2 same. And this thing is 3 plus 1, 4 by 2, it means gamma of 2. It will be 2. Okay. So now this thing becomes 1/2. Gamma of 1/2 is square root of pi. Square root of pi. And gamma of 2 is I think 1. Then we are done. This is going to be pi by 2. You can I think evaluate this thing with the help of trigonometric form of beta function as well, because trigonometric form is very good, because in that one we have sine and cos, and integrals involving sine and cos are very easy as compared to these. Okay, if there is no any question, then we are moving ahead with what we call Laplace transform. And one last thing about gamma function that I want to do right now is what we call the how the graph of gamma function looks like. So you know very well the problematic situation is 0. The problematic situation is 0. So at 0 basically it is going to be undefined, then it's defined for all the values. This is the problematic situation. And then the problematic situation is -1 and -2 and -3 and so on. And when you see, this thing will look like this. Between 0 and -1 the graph will look like this. when between minus 1 and minus 2 the graph will look like this, it means exactly at minus 2 it's going to be undefined. Then in this interval the graph looks like somehow this. So this is what we call the graph of gamma function. It's not the exact one, but it looks like this because exactly at 0 or minus 1, minus 2, minus 3 it's going to be undefined.